Good morning, good afternoon, and good evening, everybody. I'm John Storpert, the Principal Director for Marine at ICS, and I'm delighted to be your moderator for today's ICS Leadership Briefing. Efficient and quiet technologies for ships are becoming increasingly important as the industry seeks to improve performance and reduce environmental impact. Today's discussion will look at the opportunities already available to achieve reductions in underwater radiated noise as a co-benefit of efficiency improvements. And we'll also have a groundbreaking case history to share with you on the subject. So without further ado, I'll turn to today's expert panel to help guide us through the current opportunities for reducing URN and the efficiency gains that can be achieved. Before I do formally introduce them, I'd just like to remind everyone that the discussion will be recorded and made available to registered participants after the meeting. We'd actively encourage you to participate by asking questions using the question function on your control panel. And thanks to everybody who has submitted questions in advance. So to our panel. First, I'm delighted to welcome my colleague, Chris Waddington, our technical director here at ICS, and our expert on underwater radiated noise. Welcome, Chris. Next, warm welcome to Stefano Gaggero, Associate Professor at the University of Genoa. Welcome, Stefano. Next, an equally warm welcome to Alessandro Marino, Naval Architect at Fincantieri. Welcome, Alessandro. Also joining us today is Savas Sezen, Senior CFD Specialist at Lloyd's Register. Welcome, Savas. And to complete our panel today, we have Göran Grunditz, Director of Hydrodynamics at Kongsberg Maritime. Welcome, Göran.
Thank you.
So, Chris, if we could perhaps start with you just to give us a brief overview and perspective from ICS on this subject.
Thanks very much, John. And first slide, please. And next slide. So, good day to all. Thank you for joining us today. And as a lead into the discussion, I'd like to respond to these three questions. Firstly, why do we need efficient and quiet ships? Of course, shipping needs to decarbonize, and there are already international regulations in place that are incentivizing energy efficiency. And these include IMO's Energy Efficiency Design Index and the Carbon Intensity Indicator, which are both progressive regulations. It's generally accepted that about a third of our net zero by 2050 goal will be achieved through these efficiency gains. The need for reductions in noise is perhaps less well known. Underwater noise radiated by ships, also known as URN, can travel great distances and accumulates as a background hum of ambient noise that is inhibiting the day-to-day activities of marine life. For example, hindering its ability to communicate, navigate, hunt, and reproduce. And to use an analogy, it's difficult for humans to communicate effectively when we experience noisy road traffic. And for marine life, URN generated by shipping is having a similar effect. This is of increasing concern, and it's important for industry to be aware of this impact and to take reasonable steps to reduce URN. To respond to the question how, let's turn to the second slide now, please. This pie chart summarizes the result of a study by the consultant VARD, and this study was sponsored by the Canadian government. VARD identified a long list of over 100 energy efficiency measures that are available to ship owners and evaluated their impact both on efficiency and URN. The very large sector to the right, occupying about 2/3 of the chart, is those measures where there was clear synergy between efficiency and URN reduction, i.e. efficiency measures which not only reduced fuel consumption, but also reduced URN. For example, wind-assisted propulsion, air lubrication, hull cleaning, more effective anti-fouling, bulbous bows, speed reduction, etc., etc., etc. The quarter segment to the top left represents those measures where there was insufficient data to decide. And the very slim dark blue sector at around 8 o'clock is for the very few measures where there was a potential conflict. That is, where increases in efficiency could potentially increase URN. For those measures within the largest segment, that is from midnight to 8 o'clock, the greenhouse gas regulations are already incentivizing ship owners to adopt these. And this will accelerate due to the progressive nature of the greenhouse gas regulations. So that is very good news, and it will inevitably lead to URN reduction. And it represents an opportunity for industry to readily reduce URN simply as a co-benefit. And to further demonstrate this beneficial effect, I can also refer to the recent Navison study sponsored by the European Maritime Safety Agency. This study forecast URN levels for European waters through to 2050. And a scenario considered was where ship owners are only incentivized by the greenhouse gas regulations to adopt energy efficiency measures. And there was no separate incentive to reduce URN. The overall result was a reduction of URN sound energy of about a third. So this aligns very closely with the observation I just made. That is, although the greenhouse gas regulations were configured to achieve IMO's greenhouse gas reduction strategy, an unintended consequence is that they are also likely to produce welcome reductions in ambient URN. Nevertheless, let's try and do even better than that by focusing in on that narrow blue sector and see what can be done to minimize the conflicts. Within that sector lies both propeller design and propeller operation. Propellers are important as they are the dominant source of URN emitted by ships, particularly from cavitation. So minimizing their impact is a very effective way of controlling URN. Therefore, our webinar today will put these aspects under the microscope and will invite our experts to guide us to the best propeller solutions. And lastly, the question of when, i.e., when should industry act? Ship owners are already adopting energy efficiency measures, and some quite large fleets have already undergone major upgrades, and this upgrading will only increase. There is also a continuous flow of orders for new ships. If URN is considered in parallel with the need for efficiency, then URN reduction becomes straightforward and part and parcel of efficiency upgrade programs and new builds. But if considered as an afterthought, it will be much more difficult to retrofit our way to URN reduction. Therefore, the time to act is right now. And at this point, I'll hand back to John. Thank you, John.
Thank you very much, Chris. That was a really helpful setting of the context for our discussions today. Stefano, could I now turn to you to give a brief overview of what cavitation is and why it creates so much noise?
Yes, of course. Thank you, John. So basically, cavitation is a phase change of water. In a way, it is similar to boiling because liquid water turns into vapor. The difference, the basic difference, is what causes this change. In boiling, water vaporizes because the temperature increases. In cavitation, instead, the temperature remains essentially the same, but the pressure drops. And when the local pressure falls below the vapor pressure of water, vapor bubbles are formed. And this is particularly important for propellers because a propeller generates thrust through a difference through a pressure difference between the face side and the back side of the blades. And the back side naturally operate at much lower pressure. So this is where cavitation usually begins. And the risk becomes even greater when the propeller is heavily loaded or rotating at high speed. The formation of these vapor bubbles is the main source of underwater radiated noise from a propeller, because the key point is that cavitation is an inherently unsteady phenomenon, and this unsteadiness can be observed at two different levels. The first one is what we can call a kind of macroscopic scale, because the pressure distribution over the propeller blades is not constant, because the inflow to the propeller is not uniform. It is affected indeed by the ship weight, which continuously changes the pressure fields as the propeller rotates. As a result, the cavitation bubbles grows and then collapse repeatedly during every revolution of the propeller as they move into regions of higher pressure. And this periodic behavior generates a distinct tonal noise at blade passing frequency and its harmonics, which is superimposed on the tonal noise that is already present even when the propeller is not cavitating. But probably the most important aspect is the second type of unsteadiness, which occurs at a microscopic scale. On the surrounding of this primary vapor bubble, around each cavity, water is continuously evaporating and condensating. And this process constantly produces an enormous number of very tiny vapor bubbles. And as soon as these bubbles enter the region where the pressure is high enough, they collapse almost instantaneously. Each of these collapses release a small amount of acoustic energy, but because of millions of these events that occur every second, together they generate the broadband noise that characterize cavitating propeller. So in practice, cavitation can be considered probably the most important cause of underwater radiated noise, because it produces both tonal noise due to the periodic growth and collapse of the cavity over each blade revolution, and broadband noise due to this continuous collapse of microscopic bubbles. So these are basically the physics of cavitation and the reason of radiated noise.
Thank you very much, Stefano. That was very, very clear and very interesting. Turning to Alessandro now, apart from cavitation, are there other sources of noise from a propeller, and what can be done to manage them?
Thank you, John. So next slide, please. There are indeed, while cavitation is the main noise source from a propeller, there are indeed other elements. As you may see here, they are summarized quite briefly. First of all, we got the flow noise. So the flow generated by, the noise generated by the flow going around the hull, the shaft line, or pod, on anyway the system that is installed, and the propeller itself. But this is a secondary element. We got the blade rate, because we have an item moving in the fluid, so that can be, of course, mitigated by reducing the speed, but then one has to compromise on the performance on the ship and so on. The propeller singing, which is basically a single tone generated by vortices shed from the trailing edge of the propeller blades. This comes to the propeller design, so it is possible to reduce or actually extinguish this source of noise by properly design an anti-singing edge, which basically is a sharp trailing edge that breaks these vortex structures from the trailing edge of the blade. And then, of course, as Stefano very well described, we've got the cavitation, which is the main source of noise from a propeller. Thank you very much, John.
Thank you, Alessandro. That's very, very helpful and very clear. Savas, you've published some guidelines for ship owners and operators on reducing their URN whilst simultaneously improving energy efficiency. Can you summarize what those recommendations are for us?
Yeah, thanks, John. Yeah, absolutely. One of the key messages from our guidance is that the underwater radiated noise and the efficiency should be considered together, like rather than as separate objectives. I mean, as Stefano explained at the beginning, the biggest contributor to underwater radiated noise is typically the propeller cavitation. So many of the measures that improve the propulsion efficiency can also reduce the underwater radiated noise. So we therefore, recommend starting with the fundamentals, like maintaining a clean hull and the propeller, managing biofouling, and ensuring the propulsion system is operating, let's say, efficiently. These measures reduce resistance, fuel consumption, cavitation, and associated noise. We also highlight the importance of, let's say, understanding the vessel's operational profile. A ship's speed, let's say, loading condition, draft, trim, all influence the propeller's loading, cavitation performance, and ultimately both efficiency and underwater radiated noise. So, for example, a solution that works very well for one condition and one specific vessel may not be the optimal for another condition and another vessel. So for that reason, when considering a new propeller or energy efficiency technology, we recommend optimizing the package as a complete instead of separating them. So using CFD, model testing, sea trial, and performance, monitoring, owners can really identify the solutions that improve the inflow quality, reduce cavitation, and associated underwater radiated noise. So this will eventually, show the benefits of both fuel efficiency and underwater radiated noise. So the overall, the recommendation from our guidance is to take a holistic approach. First of all, understand the vessel's operational profile and understand how the vessel operates, and optimize the propeller together with the energy efficiency technology, and evaluate let's say, the efficiency and underwater radiated noise together. Thanks, John.
Thank you very much, Savas. There's some interesting points there about other measures that, because they contribute to efficiency, also have a knock-on effect on the impact of underwater radiated noise and underwater radiated noise emissions from ships, and particularly, I think, the context of biofouling, which of course is another significant topic under consideration at IMO at the moment.
Exactly.
So, turning now to Goran, you've had real-world experience in a very effective propeller upgrade on the Baltic Queen ferry. So, can you share some of the key points of that upgrade and what your findings were?
Absolutely, John. The Baltic Queen represents a very typical Ropax ferry operating between Stockholm, Mariehamn, and Tallinn, as you can see on the chart to the right. And this is a good example and a very typical example of a Ropax ferry and how they normally are built. And this will also lead us into the discussion around propellers, and especially controllable pitch propellers, and how they are operated and how that will affect noise levels. So the ferry is designed with, it's a twin shaft system, conventional shaft line propellers and rudders, and it's 2 main engines per shaft. The ferry is designed for 24 some knots, running on 2 engines per shaft, but it also takes into account the fact that it at some occasions will operate with only 1 engine per shaft. And that is going to affect the propeller. So if we go to the next slide here, we can see how that is affecting the propeller. But first, we want to introduce you to the PDN diagram, which is very crucial to understand how a propeller is being operated. So on the x-axis here, you have the propeller speed, and on the y-axis, you have the propeller power. And you have curves for constant vessel speed, and you have curves for constant pitch of the propeller. So you can see on the speed curves that the efficiency varies with the pitch on the propeller. And if we go one step forward here, you can see that 85% of the power, that's typically where the propeller is normally being designed. It's 24 some knots. You operate with 2 engines per shaft. You have basically the maximum shaft speed. But then, as I said, for some occasions, you want to operate with only 1 engine per shaft. You maybe have parts of the routes that is that where you have lower speeds, so then you can disengage one of the engines. And if we move one step forward here, you can also see to be able to operate with only 1 engine per shaft, you need to retain the shaft speed. Otherwise, the single engine will not be able to handle the torque on the propeller. So we are reducing the pitch of the propeller quite significantly, keeping the shaft speed, and in that way you can disengage one of the engines. You still do some 19 knots. And for the Baltic Queen, we realized that they are basically operating most of the time on the road between Stockholm and Tallinn with only 1 engine per shaft. And if we proceed one step further here, we see that that also means that you're operating in an area where you have risk of having cavitation on the pressure side of the propeller blades. So constantly operating with very high shaft speed, very low pitch means you get risk of having pressure side cavitation, which typically is a very noisy type of cavitation also. So what we did here for this, we offered Tallink new propeller blades that was designed for 1 engine per shaft operation. Means that we are getting rid of the pressure side cavitation, getting a significant drop in underwater noise levels. I think the achievement was some 8 decibels in reduction at 19 knots. And at the same time, we also increase the efficiency of the propeller quite significantly. And that you can see by looking at the diagram. So instead of operating at 19 knots with a lower shaft speed with 2 engines per shaft, with a shaft speed of 110 revs per second, for example, compared to 150 revs per second, you can see how much more power you need to put on the propeller to achieve 90 knots. I think it was like 13 to 17% lower fuel consumption after the upgrade. So this is a very typical good example of what we can do to upgrade existing ships with a new propeller, reducing both URN levels and also increasing the efficiency of the propeller, reducing fuel consumption. So basically here we can see that URN and efficiency goes hand in hand. And if we move one step forward here, as Stefano, Alexandro, and Savas talked about, it's the inflow to the propeller is very important. This is a single screw vessel, so it's not the same as the Baltic Queen, but the principle is the same. So the water is being dragged by the hull. You get an undisturbed flow into the propeller. So for a single screw, you can have a wake peak of that could be as severe as you have water velocities of 20-30% of the ship speed coming into the propeller. So if you should aim to reduce the power consumption, the fuel consumption at the same time as you are reducing underwater noise, you need to consider this from the start of the design of the vessel. You need to make sure that you have a nice and smooth inflow to the propeller. You have a good wake field, and then you can also achieve good efficiency at the same time as you get a very, very low levels of noise. Because if we move one step forward here and overlay a simulation on to the wake field here, we can see how the cavitation builds up when the blade passes through this wake field that is caused by the hull, and then it disappears again. So this is what Stefano and Alessandro explained. So if you have a smooth and nice inflow to the propeller, you will get less cavitation, also meaning that you will get less noise levels. Thank you, John.
Thank you very much, and thanks to all of our presenters for very, very interesting contributions. Please keep the questions coming in. We have lots and lots of time for questions and further discussion today. So I'll turn to our panelists now with some of the questions that we received before or in advance of the webinar. So Stefano, if I could go over to you first. For fixed blade propellers, why is there a conflict between efficiency and underwater radiated noise?
Thank you, John, for the question. And I would say that this conflict is not really limited to fixed blade propellers. It is exacerbated in the case of fixed pitch propeller, but it is a fundamental challenge for almost any marine propulsion system, because a propeller is most efficient when it produces the required thrust with the smallest possible energy losses. And to achieve these these small losses, designers typically aim for relatively high blade loading, especially near the blade tip, and they also tend to use fewer blade, low expanded blade area ratio, and geometries which are carefully optimized for only one very specific operating condition. And however, these design choices also makes cavitation more likely. As we discussed, the higher blade loadings means lower pressure on the suction side of the blade, then higher risk of cavitation with all the consequences in terms of radiated noise in both tonal and broadband. If instead the load is distributed over larger blade area and the blade tip is more lightly loaded, the likelihood of cavitation is reduced. The drawback is that the larger blades propeller generates higher skin friction losses, and the propeller no longer produces thrust in the most efficient way. So in general, improving acoustic performances comes at the expense of some propulsive efficiency losses. This trade-off is even more evident for fixed blade propellers. A fixed blade propeller is designed to operate optimally at one specific design condition, typically the ship's service speed. And as the operating condition moves away from that design point, as in the case we have just discussed with Goran, the blade loading changes, the angle of attack may no longer be optimal. The blade pitch cannot be adjusted, so the propeller cannot maintain the most favorable loading distribution, neither the most favorable pressure distribution over the blade and over a wide range of operating conditions. These, of course, increase the risk of cavitation, and in some cases, making very difficult to achieve high propulsive efficiency and low underwater radiated noise simultaneously across the entire operating envelope in the case of fixed pitch propellers. So basically, these are the reasons.
And there's a lot of them. Thank you, Stefano. Just turning to Goran now. So we know that reducing the revolutions of a fixed blade propeller improves the fuel efficiency and the URN, but is it also the case that reducing revolutions on a controllable pitch propeller can increase the URN, and what measures can be taken to minimize that?
As long as you operate with a constant pitch, the controllable pitch propeller will behave as a fixed pitch propeller. So slower speed will reduce also noise levels. But if the thing with a controllable pitch propeller, and maybe one of the advantages is that you can, as we saw on my example, you can basically play around with the configuration, the engine configurations, and you can run with a constant shaft speed. And when you run with a constant shaft speed and reducing your ship speed, you need to reduce the pitch, and then you end up in these situations where you have cavitation on the pressure side. And then the propeller becomes noisy, and this can be a little bit confusing. So reducing ship speed in such scenario means that you're actually increasing noise levels instead of reducing it. So it's important to be aware of how you operate your controllable pitch propeller and make sure that you know what you're doing in a way. Make sure that you operate your propeller in the right way.
So just to come back on that and thinking about some of the measures that are assumed to be of benefit in terms of reducing URN, in fact, in certain specialty areas with certain ship types and certain propeller types, reducing the speed might actually be counterproductive, and you need a more agile approach to how you manage your URN than what I think certain regulators, and I think we'll come back to the regulatory framework later on, but certainly what certain proponents of PSSAs and marine protected areas assume.
Exactly. So if you operate your controllable pitch propeller in the wrong way and reducing speed, you're going to increase your noise levels instead of actually reducing them. Well, if you operate on a constant pitch setting instead and reduce the shaft speed when you're reducing your ship speed, then you would also reduce your noise level as with a fixed pitch propeller.
Thanks. And I think that's going to be very interesting when we start discussing this at the International Maritime Organization, and particularly in the context of MPAs when we get around to that. But we'll touch on that a little later on, I think. So, Alessandro, if I could come to you now, and again on a similar tack, if speed's reduced, does cavitation reduce? And if so, is there a sweet spot where we can stop cavitation altogether?
Thank you, John. Well, as the colleagues already mentioned, I would say yes and no. Of course, a steel propeller does not cavitate, but eventually it comes down to the design of the propeller. If a propeller is badly designed, it can cavitate also at low speeds, and then it doesn't serve its purpose. So, of course, reducing the propeller revolution rate does have an effect, but I wouldn't consider that as the main solution to reduce cavitation. It is much more important to properly design the propeller, considering the operating profile of the ship. So, as it has been mentioned already, the wake is very important. Hence, the speed that the flow speed that the propeller perceives, and hence the angle of attack, the distribution of the pitch of the propeller, eventually the loading on the propeller. So a properly designed propeller is as unloaded as possible, and that helps reducing cavitation and makes the propeller more efficient.
Yeah, so thanks, Alessandro. So yeah, as we've heard, really, it's important that this is addressed at the design and the building phase. It's rather than by piecemeal measures throughout the operational life of the ship. And I think certainly as we go forward with our work, that is something that we'll want to emphasize both to owners who are buying ships, but also to the shipbuilders themselves, who may not be aware of the importance that is being placed on this issue at an international level, and certainly at the level of overall environmental impact in the ocean basin. So, Alessandro, if I could come back to you, and
Sure.
we have touched on this again. How can we design the fixed blade propeller to get that best compromise between efficiency and URN reduction?
Thanks, John. So if we can have a look at the slides, I got maybe something you have already seen, because I prepared a slide which shows something that Göran coincidentally has shown already. 2 slides back, please. Nope. Right.
Perfect.
So yes, a propeller works well with its own ship. So the key points, I would say the key thing is to design the propeller thinking of the ship design overall. Here we see an example of the wake perceived by a propeller with a conventional shaft line, and that's the first item to address. What conditions the propeller is going to work in, so how it is going to feel the water, and what angle of attacks it's going to work with, and so on. Next slide, please. So in order to have holistic approach to the propeller design, one has to consider, as I said, the wake before the propeller, and that can be optimized by optimizing the hull shape, which of course contributes to a lower resistance of the hull overall, and so a lower load on the propeller, which is again another factor helping decrease the risk of cavitation. Some key things that we try to apply all the time in our daily work is, for instance, to try and have the center of buoyancy as far forward as possible, so to distribute the volumes of the hull, so that the performance of the ship and the wake favorable to the propeller. Optimize the blade number, and we learned from our extensive database that for cruise ships, for the ones that we mainly design, this is actually 6, so it gives a good compromise in terms of area ratio, expanded area ratio, and revolution rate, load on the propellers, and so on. Which, of course, then we come down to the propeller itself, to the design of the propeller itself. So trying to reducing the cavitation on both sides, of course, decreases the radiation of noise. And another item which is very important is to optimize the design of the propeller in order to have low tip vortex phenomena, which is another source of radiated noise. So just to summarize, basically it's not the propeller alone that has to be optimized, but the design of the ship with the propeller as a whole.
And thank you very much, because that really leads nicely into my next question. I think I'll go to Savas for this, but maybe some of the other panelists have views on this. So we've focused very much on cavitation. We've focused on propeller design and how that functions within the overall design of the ship. But are there any other devices? Are there any other techniques? I mean, we talked about the impact of biofouling, and I think I'll come back to that. But what devices or techniques can simultaneously improve energy efficiency and reduce URN? So Savas, I'll go to you first, I think, with that one, and then maybe
Yeah,
fire it over to Chris.
Yeah, thanks, John. Yeah, definitely. I mean, while the propeller optimization is often the biggest opportunity, you know, to increase the efficiency and reduce the underwater radiated noise or vice versa, there are also other techniques and energy efficiency technologies that can improve both energy efficiency and underwater radiated noise. I mean, as Göran showed in his example, like when we improve the flow at the propeller plane, when we, you know, like send more uniform flow, actually we improve a lot of things. For example, like when we talk about the energy efficiency technologies, mainly ESDs, like we have free swirl devices such as stator fins and ducts. So they make the flow, you know, like more uniform. And in this way, we reduce the blade loading fluctuations, and this helps to delay or mitigate the cavitation. Similarly, we have post, let's say, swirl devices such as rudder bulbs and propeller bosscap fin. These devices also recover the energy in the propeller's wake, and they also contribute to, let's say, the efficiency and underwater radiated noise. So apart from these energy efficiency technologies, as we all know, like slow steaming is important thing to increase the efficiency and underwater radiated, decrease the underwater radiated noise. And we have, you know, like hull optimization, which is very much important in terms of wake. So we have wind assisted technologies, which is of great interest nowadays, and we have air lubrication. We have new ESDs called gate rudder. So, and then, you know, like mainly we can do trim optimization to improve the wake field and propeller's performance and hence the noise. So, but when we do like all of these things, the important point is how we will be able to match these energy efficiency technologies to the vessel's operational profile, because these are, I mean, this should, everything should be, you know, like compatible with the vessel's operational profile. For example, I mean, the effectiveness of these technologies really depends on the depends on how the vessel operates. So it is speed, loading condition, draft trim, and everything. So that is the reason why we recommend evaluating this solution on a vessel specific, as I mentioned at the beginning of the presentation, like using CFDs, model testing, and full scale trials. So like as you said, John, like beyond these energy efficiency technologies and all other things, there are also some operational measures. Like, to be honest, like the simple thing is like maintaining a clean hull and the propeller, managing biofouling, and operating the vessel efficiently can reduce the resistance and lower power demand and reduce the cavitation. And this will deliver, you know, like benefits for both fuel consumption and underwater radiated noise.
Thank you, Savas. I'll pass over to Chris, but I do have a follow-up question on this. And again, if any of the other members of the panel want to chip in, please feel free to do so, because this is a fascinating subject and a fascinating conversation that, whilst we're talking about URN and efficiency, it touches on so many other areas that the IMO in particular is looking at the moment, and also the developing technologies as we work towards net zero. But Chris, I'd just be interested in your views on this, given what you said at the start.
Yes, thanks, John. I think Savas got most of the items on my list, but I think a key thing there is just the length of the list. You know, there's quite a few things we can do to the propeller design itself, but there's also a lot of things we can do around the propeller, particularly with respect to flow straightening and getting that wake flow into the propeller as clean as possible. Another one I had was use of composite material for propellers. That's been found to be effective in reducing the noise from the propeller. Propeller cleaning, very simple but effective. Speed, for sure, that's effective, particularly when you drop below the cavitation inception speed, which is normally about 10 to 12 knots. If you drop below that, basically the cavitation turns off, it disappears. There is some issues around speed, though. Of course, capacity. If we slow down too much, then it becomes a capacity issue, and we have to build more ships to carry the same amount of cargo, and then, you know, you've got an impact from those additional ships. But there is some systems being looked at called just-in-time arrival, where the systems try and eliminate port waiting time. So you configure the speed of the ship going transocean trying to get the ship to arrive just in time to offload the cargo. So you're minimizing the speed whilst still carrying exactly the same amount of cargo. So those look really interesting. There's a consortium, in particular, there's a consortium called Blue Visby. They've got a website you can look up, and they've got a very interesting concept around this. Another thing to note, some of these devices like propeller boss cap fins, flow straightening fins, etc., there are some environmental incentive schemes now which are specifically geared up towards those. For example, the environmental incentive scheme in Canada, in Vancouver, they have a list of some of these devices, and if a ship owner can demonstrate that they are using these, then they qualify for discounts on port dues, which are quite generous. So there's a financial benefit potentially to some of these. Thanks, John.
Thanks, Chris. And I think the just-in-time arrivals piece there is very important when we're talking about not just URN but efficiency in general and slowing down ships, because I mean, we've had this debate all throughout the energy efficiency debate, but what regulators fail to recognize sometimes is the commercial imperatives that drive ships. We tend to silo our thinking just down to the issue of URN, just down to the issue of efficiency, and they forget that, you know, the terms of the charter party might be very, very strict on how you operate on any one voyage and the knock-on effects of that. So it is, I think it's an area that is going to be extremely interesting as we go down this path towards decarbonisation, and we get new fuels on board, new technologies to improve the efficiency of ships. That assumption that just slow down will make everything better may not necessarily be the right one. Also, in the context of ship design, I wonder about, you know, reducing the drag on hulls. What are we going to see in the coming years in terms of coating technologies and other technologies that improve efficiency further there? Because again, it's an area that is often out of sight, out of mind, but it's fundamentally important to the performance of the ships. And I think in particular in the associated work that we do on biofouling, that really needs to be drawn out. We really need to hear from that sector and what they're planning for the future. Perhaps a cheeky question or a naive one, I don't know which, but we've associated the reduction in URN with an increase in efficiency, and obviously a knock-on effect of that is that your fuel efficiency goes up and you use less fuel on your voyage. Given it's difficult to actually record or monitor the URN emissions from a ship while it's underway, could we, and I'll open this up to the whole panel, can we work on an assumption through performance monitoring throughout a voyage that greater fuel efficiency is an indicator of reduced URN, or is it more complicated than that? I don't know who wants to.
It's a bit more complicated than that, of course, but in general terms, if you reduce your power consumption, you're also going to reduce the loading on the propeller, and you're going to reduce the amount of cavitation. Generally speaking, that is yes, but then we have seen how you operate your control, which propeller is going to be of importance. So obviously it has another dimension as well.
Thank you. I think we've probably got time for maybe one more question, and I'll direct this to Chris. So obviously you've been very heavily involved in this subject at the regulatory level. We've assumed that there was something coming over the horizon on underwater radiated noise reduction for a couple of decades now. I think it was, you know, at the start of my career when this was first raised at IMO, but nobody really knew how to address it, how even to monitor it back in those days. I think we're much further down the line in terms of being able to monitor it, but also in understanding how ships produce noise and how we can mitigate it. But without wanting to put you on the spot too much, what is the mood at IMO on this subject? What work is being done, and what is being planned in terms of maybe a regulatory framework to deal with the issue of underwater radiated noise?
About 3 years ago, IMO updated its guidelines on underwater radiated noise and then entered an experience building phase for those guidelines. And an important aspect of those is the idea of a noise management plan. Each ship should have its own noise management plan. We've got a further 2 years now of the experience building phase, and there's work actively going on to try and figure out how we can increase the uptake of these measures, and in particular the noise management plan. Looking forward, there is a proposal to carry out a forward-looking study on the global levels of ambient URN through to 2050, and to look at different scenarios. You remember I mentioned the Naviton study at the start. So similar to that, but at a global scale. And this is something that we have supported. You know, we think it's important from a policy point of view to understand the impact, particularly of the greenhouse gas regulations going forward. I think another really key thing going forward for ourselves, industry, is how do we measure ships at an individual ship level? Because to put in place an effective noise management plan, it's necessary to measure the ship, preferably several times, you know, throughout its life. And the cost of doing that per ship at the moment, with a dedicated sea trial, where we have to set up a series of hydrophones, is somewhere between $30,000 and $50,000. So we're looking at the moment at more practical, more accessible ways of doing that. And there is some autonomous facilities. There was one at Genoa, there's 2 in Canada, which automatically record the URN emitted by ships as they pass. So it's very easy for the ships. They don't have to redeploy to a trials area. The equipment's already there. So it could be something like that in the future. But we think this is really important. You know, we cannot manage what we can't measure. So logically, the first step, we think, is to get in place reasonably economic, accessible means of measuring the ships. Thanks, John.
Thanks, Chris. And I think that fits with the sort of direction of travel that we're seeing at IMO on a number of subjects now. Experience building, monitoring, understanding the actual impact is increasingly being seen as essential, rather than, and maybe it's the experience of certain other instruments, which I won't mention here, but rather than going bullheadedly into let's regulate, understanding how shipping works and what the impacts of technologies and new technologies are, is increasingly seen to be important in that regulatory context. So I think overall, this is a very, very positive work stream. It's a positive development, and industry and regulators are working together hard to ensure that what we do is proportionate and effective. We've got 7 minutes left, but I think we'll start to wrap up now. So I'd just like to give each panel member a minute or two, just to give 3 points on key messages they'd like our audience to remember from their presentations and our discussions today. So Savas, can I start with you, please?
Yeah, sure, John. Yeah, thank you. Yeah, first of all, like the first one is, I mean, we should really understand that there is no one size fits all solution, because the optimal answer really depends on the vessel's operational profile, loading conditions, speed range, etc. So understanding the how the ship operates is very much important, you know, like before selecting any technology to improve the efficiency and reduce underwater radiated noise. The second thing is, like, we really need to have a holistic approach. I mean, like, we may have a, you know, like, new energy efficiency technology to increase the efficiency and reduce the URN, but for example, the hull cleaning is still important, propeller cleaning is still important. Like, we should really think about all of them as a package. So we should really optimize everything at once, instead of looking at one technology. The third thing is, the last thing is, for this is like the cavitation. I mean, although in some cases it can be different, but cavitation, I mean, can be considered like a common link between the cavitation and underwater radiated noise. So if we can reduce the cavitation through better propeller and propulsion system design, we can often, like achieve lowest noise levels and lower fuel consumption and lower emissions at the same time. As I said, but it's really, like this situation is a bit different for controllable pitch propellers, as Göran mentioned. So this is all from me, John.
Muted, Jon.
And I was doing so well. Alessandro, over to you for your views.
Thank you, John. Yeah, from my point of view, well, first of all, the first key point is that we know that URN has an impact on the environment the ships work in, and they have a huge impact on wildlife and so on. And so we're going into the right direction by taking actions to reduce the impact that we have on wildlife. And that's a good start, I would say. Then the main key point, in my opinion, is, as we've already mentioned many times, that the focusing on propellers only as a source of noise could be misleading. So the approach must be holistic and as broad as possible in order to understand the sources that contribute to the propeller generated noise. And finally, but linked to this key point, it's I think it is important to consider other sources of noise that are related to ships. We mentioned many times fouling on both the hull and the propeller. The growth of fouling actually creates an alteration on the surfaces of both ship and propeller, which definitely has an impact on the performance overall, but also on the noise emission performance. By changing the shape, at the end of the day, one does change the noise generated by the propeller.
Thank you very much. John. Thank you, Alessandro. An excellent point there. Stefano, you have the floor.
Thank you, John. So my points are very similar to those of Savas and Alessandro. If I focus on propeller, remembering that they must be considered as only one of the part of the entire ship, I think that we need to always consider cavitation as probably the most important indicator of noise, especially because in the design process it is very difficult to address noise directly, so we need some proxy to detect the occurrence of noise or to quantify the noise. And in this respect, I think that we should progressively move towards a kind of robust design approaches in a way such that we do not focus anymore on a very specific functioning point, but just to take into account the entire vessel life, the entire operational profile of the ship. It is better to, in the design approach or in the optimization approach of a propeller, to take into account of design condition, different functioning condition, in order to achieve or to design a better balanced propeller that probably is not the best in terms of efficiency, but it provides a more constant, less varying efficiency and over an entire range of functioning condition, granting at the same time low emissions in terms of noise.
Thank you, Stefano. And Goran, over to you for the last minute before I hand to Chris to close for us.
Yeah, thanks. Three points from my side. Work with the resistance of your vessel or the power consumption of the power loading on the propeller. Reduce resistance, make sure you have a large, slowly rotating propeller as possible. Ensure you have a smooth and nice wake field coming into the propeller. That will help you a lot. And when it comes to the propeller design, it's mainly a compromise and optimize. It's an optimization, but it's also a compromise between efficiency and noise levels. So working with the power consumption and the wake field gives you good possibility to get a good and silent propeller as well. Finally, don't forget there is other noise sources on board as well.
Thanks, which we only touched on a little. There's a huge amount around this subject. Chris, the last 30 seconds before we close the meeting.
Yeah, thanks, John. I think for industry at this point in time, it is so important to raise awareness, and this webinar has been great in that respect. Awareness of the impact of URN on wildlife. We need to act and do what's reasonable to address this. And the opportunity here to leverage the synergies to achieve this alongside energy efficiency measures, which are mandatory. We have to do the energy efficiency, and if we do it in the right way, we can get the URN reduction as well. Dual skilling, clearly the representatives on this panel are dual skilled. They don't just think along the lines of energy efficiency or URN reduction. They think of both together, and that's how it should be. Energy efficiency is happening now. There's major programs to upgrade fleets for energy efficiency. So the opportunity is now. And I think the example that Kongsberg gave of where they simply changed the propeller, nothing else, they just changed the propeller and got improvements in fuel efficiency of 15% and 8 decibel reduction in low frequency URN. It can be as easy as that. Thanks, John.
Thank you, Chris. And a great note to end on, that solutions are out there, and we are actually some way down the road on addressing these emissions from ships. I think that was a great series of presentations on a very important topic that's going to get a lot more traction in the coming years, and there was plenty for us all to consider. So I'd just like to thank the panel for all of their contributions today, and to thank you in the audience. We appreciate you taking the time to join us today. And so now the webinar is closed. Thank you very much.
Thank you.
Thank you.